Greetings. In last lecture, we were discussing about analysis of trusses, and in that, the part related to basic assumption was under discussion. We'll continue with that discussion. Every member of truss is a two-force member. This statement says that when a member of a truss is subjected to any load here, they will have the dual action here, dual force action. For example, at this node, if I say the gravity load is applied, this geometry will try to get deformed. During this, some members of this geometry will be under a stretch and some members will come under a contraction. The member which are being stretched, they are observing a tensile force, whereas the member which is getting contract, they will observe the compressive force. It depends upon how the load is applied and where the load is applied. If this, instead of this, if I say the load is applied on this end, what will happen? This end will now get stretched, and suppose the load is applied in horizontal direction, likewise this will now stretch, and the member which were is in compression for the initial case will now become, they will act as a tensile member, so under tension, so they will be subjected to a tension pull here. A pull and push action, and reversal of this pull and push action will be there within the members. That's why the member is said to be, truss member is said to be a dual action member, and we say that the ends connections are the pin connection. Only the forces which are transferred in the member will be the force which are transferred uh, at the geometric centroid, and that is why they will be classified as a axial pull or axial push, axial compression or axial tension. That's why every member of the truss is assumed to be carrying only two forces. For example, if suppose I, instead of providing the pin connection, if I provide here some restraining end condition, due to this there will be a slight bending observed by the member. This bending will be neglected, or the special provision consideration of the bending will be considered, and thereby we will consider that the members are subjected to only axial pull or axial push or axial compression or axial tension. Let's go towards the other assumption. The self-weight of the members are neglected. As compared to the supporting system, the weight of other elements which are being transferred to the load, the self-weight of your truss is very much less. That's why it is said to be neglected, or we are not going to consider that in case of calculating the total dead loads which are appearing on it. Okay, or sometimes if it is so, then the special provisions are made made to account for the self-weight of the structure. Cross section of the members are uniform, means the cross section will not vary from member to member. Whatever the function of the member will be there, whether it is a bottom chord or whether it is a top chord or whether it is a vertical strut or horizontal member or inclined member, they are going to have uniform cross sections, so as to assure that there is a uniformity in the geometry. If there is a ununiform cross section, then what will happen? There will be unequal distribution of the stresses, and thereby it will not the validation of the your assumption will not be there. So one has to ensure that the cross section member of each element within the truss is uniform. If suppose there is a certain constraints, this uniformity is not being maintained, then it is a duty of construction engineer to see that the centroid of all cross section lie along a single axis, so that member is held in equilibrium by the two force acting at its end. So it becomes a job of construction engineer to ensure that centroid of all such cross sections are going to lie on a single axis, so that there is a surety that the members are subjected to two forces at the ends only, and they are being in equilibrium. Various cross sections which are being used in preparing trusses are the hollow square pipes, the circular square pipes, the mild steel rolled steel sections. It may be cold form or hot rolled steel sections of different shape like I shape, channel shape, angle shape, or T shape, but light in weights. Not heavy sections has been used in case of trusses, because what we have said, self-weight of truss should be very much less. Sometimes, depending upon the load carrying capacity, we require the light members also. So sometimes timber trusses has been used. for covering light small spans and light load structure, the timbers has been used. Now let's go towards the mathematical condition about a truss. A truss is said to be skeletal geometry, generally forming a triangles. So in case of a truss, we have three members connected at the ends with the pins, and in a truss we will have three end connections and three members. Okay, this is a simple geometry. If I want to increase one more element and I want to increase the span of this, what I have to do, I have to define the additional node here. If I say the additional node which I am going to define is numbered like nomenclated like j minus 3. Why j minus 3? Because this is a joint which is extra than the previous which is available. The truss in its basic form have the three joints in it. So what the next joint number will be j, that is the j number j minus 3. How we will get the j number here? J minus 3. Suppose I want to put here 4. What I will do here, 4 minus 3 means this will be the definition of this particular joint. If I want to define such a joint, I have to connect this joint with the help of two members. So how many members I am going to require for a extension of a truss? I require one joint and two members. Can I say for the j minus 3 joint, if I have two members, 2j minus 3 members I will require. So that's why now this is what we can say. This is the new format which we have obtained. We have extended the truss. So let's see about the compatibility of the members here. So total members in a truss will be now equals to m dash plus m double dash. So I can write it as a m dash is nothing but basically we have 3, and m double dash is nothing but based on the joint. In this simple geometry I have put here one joint. There may be n numbers of joint. So what I will do? It will be number of members required to connect one joint, that is 2 into j minus 3. For increment of one joint I will require 2 into j minus 3. If I expand this, I will get m equals to 3 plus 2j minus 3. I have expanded this one, this bracket. Then the resultant will be m plus 3 equals to 2j. Okay. So what we can say, we have defined equations which state about the number of members which are being present in the particular geometry and with reference to the number of joints which are being possessed by that particular geometry. So this equation will define whether my truss is being the perfect truss or it may be having certain deficiency. So based on this, m plus 3 equals to 2j. If this equation is being satisfied, then I am going to call it as a perfect truss or rigid truss. If m plus 3 is greater than 2j, means there is an excess of the members in the geometry, then I am going to call it as a redundant truss or over rigid truss, where I have to reduce the member or I have to remove one of the constants from it. M plus 3 less than 2j. M plus 3 means the number of members requirement is less than the number of joints which are required to define the truss. Then I am going to call it as a deficient truss or collapsible truss. To make adjustment, either in case of redundant truss I am going to reduce the member, and in case of deficient truss what I will do, I will add the members to it. So this what we call it as a compatibility of the members within a truss. Now let us extend this with the help of some numericals, work out with the help of some numericals, so that the complete understanding of the mathematical conditions will be there. Numerical states that evaluate whether the truss shown in figure is perfect or not. If not, then what type of imperfection it bears. So we have to identify whether it is a perfect or not, and if it is not, then we have to define what type of imperfection it bears. The structure is given is like this, having a support system. One end is being hinged, other end is being supported by a ruler. Now what is our job? To have the identification whether it is a perfect or imperfect. For that, let us define how many joints are being there. If I count the number of joints here, the number of joints count is about 6. Then I will have a count of number of members here. The count for number of members is 9. So if I put this in equation, m equals to 2j minus 3, what I have written there in a reverse format. M plus 3, I have taken 3 on that side, it becomes minus 3. M is equal to 2j minus 3. If I substitute the values here, 9 members, 2 into number of joints are 6. minus 3, it gives 9 equals to 9, means both the side of equation is balanced. Then I am going to say the truss is a perfect truss. Okay, now let's have the second example here. A truss is being supported by a supporting system. One end is hinge, other end is at a roller support, and the member geometry is shown here. Let us have the count of joint. Joint counts is j equals to 4 joints, and the member counts are m equals to 6. So here at the overlapping of the two inclined members, there is no connection defined. So I'm not defining any connections here, any joint here. That's why joints are at the corners only. J equals to 4 and m equals to 6. So m equals to 2j minus 3 will result 6 equals to 2 into 4 minus 3. 5 equals to 4. Means here number of members are extra, and that type of deficiency we call the truss is imperfect and deficiency is redundant frame. Means here we have extra members. We can make it determined by removing one of the member. Okay, next example, it's a truss shown here in the figure supported by a certain system and restraints, and we want to define whether it is a perfect or imperfect. Let's have a joint count here. Joint count is 4. Number of member count is also 4. That's why m equals to 2j minus 3. 4 equals to 2 into 4 minus 3. 4 equals to 5. What is the meaning of this? Number of joints are more compared to the number of members available in the truss. Thereby, it's going to define that the truss is imperfect and it is a deficient one. Okay, so this deficiency, what we have to do, either we have to add a member here, or either we have to release one of the end support end restraints here. Okay, so this type of deficiency is called as a your collapsible deficiency or deficient truss. Now let us try to classify this truss. The truss assembly is given. The two base has been defined here. One base has a cross bracings, another base is only simple a square geometry. Let us try to first identify whether it is a perfect truss or imperfect truss. So let's say the count of joint here. Joint count is 6. Count of members count is 9, and the equation says that m equals to 2j minus 3, 9 equals to 2 into 6 minus 3, 9 into 9. It is a perfect truss. But I have put here it is deficient here. This is due to mistake. You read it as a the truss is a perfect truss only. Okay. Now let us view this one in a different direction. If I observe individually the two bases of this truss, the first truss we can say it is a redundant part, because within this bay we will find there are excessive members, and other part there is a deficient because there is a lacking of a member here. So one is collapsible and one is a redundant one. This situation arises in case of general design when there are constraints for a designer to put such a geometry. So for example, if it is a foot over bridge and there is a passage here made for the movement of the pedestrian, then it's not possible for us to provide a cross bracing here. In that case, what I will do, I have to balance the geometry. So I will remove the cross bracings here. Thereby, the truss which is itself in a geometry, it's being perfect, but it's subjected towards a question marks related to the compatibility related to the equilibrium. Here we will say the compatibility. This deficient will have a deformation, excess deformation, whereas this will have a imbalance in the force. There are two types of this deficiency arises, which we called as a determinacy and stability. Okay, so we'll deal with this part related to determinacy and stability in upcoming lectures. Till then, be at home, be safe and healthy. Thank you.